All right, let's get started. So first of all, who watched the video of this lecture? Only one? Two? Okay. Three? Good. Okay, yeah, I may go a little bit slower, so it's not very hard, but we do need to understand part of this lecture to understand today's lecture. Okay, and yeah, the other thing is that I uploaded an exercise exam. Hopefully you received it. And also I uploaded the lab 6, so which you can start right now, but the due date will be 2 weeks from now. Okay? So any questions about midterm? So midterm will start on Wednesday at 9 a.m. and then will be due on Friday 9 a.m. Okay? All right, so okay, yeah, let's see what we cover in this makeup lecture. So basically we talk about two things. So one is aliasing, and the other we call that reconstruction. So basically here we mean that under the practical or non-ideal case, how can we reconstruct the signal? Okay. So yeah, this is the impulse sampling, right? So we can see on the top, so that is basically the frequency representation of the impulse sample signal. All right, so basically it looks like this, right? So let's say this is our original signal. We need to reduce it by t times or ts times, and then make it periodic, right? The period of the signal is omega s or fs in hertz. Okay, so this is our sample signal. Okay, so to recover the signal is relatively straightforward. We just need to use a low-pass filter on top of this guy and filter everything out, and then we're gonna have a perfect reconstruction of the original signal, right? But the constraint here is that the signal has to be band limited, right? It has a maximum frequency. In other words, the sampling frequency has to be bigger than 2 times the maximum frequency of the signal. Okay, so otherwise there will be overlapping, and we cannot recover our original signal. And this sampling rate, 2 times omega max or 2 times the B max, or 2 times the bandwidth, is called the Nyquist sampling rate criteria. Okay, and 2 times omega max is called the Nyquist sampling rate. Okay, and if we cannot satisfy the Nyquist sampling rate, and then we have to have aliasing, and here is the concept of aliasing, right? Basically, it means that signal overlapped with each other. Right? Right. This happens when omega s is less than 2 times omega max. Okay. So now we have aliasing, and in this case, there is no way to reconstruct the original signal. Okay. And in practice, this is always the case, right? So as we introduced in the 2 lectures ago, so we say if a signal is time limited, meaning that it's limited in the time domain, then it will be unlimited in the frequency domain, right? Any signal in reality is limited in time domain. So we have a starting point of signal, we have an ending point. So in frequency, in theory, so it's always unlimited, right? So perfect reconstruction of the original signal does not exist in practice, okay? And okay. So in order to get rid of the aliasing, so one way that we can do it is called anti-aliasing filter, right? So basically what we do is that we can, maybe, yeah, let's see this figure, maybe that is better. So we can pass the original signal, yeah, let's ignore all of this, the original signal via a low-pass filter beforehand, right? To get rid of the high frequency component, make it like a band-limited signal, okay? And then passing that, and then sample that, right? So that can avoid kind of aliasing, and this is how it works in practice, right? So basically, so we pass the original signal g of t via an anti-aliasing filter, so that's a low-pass filter, okay? We pass that with a low-pass filter and then make it band-limited, and then we sample that, and then we can get our sample signal, okay? So this is what we do in practice, right? So basically, we get rid of the high-frequency component and make it band-limited, right? So is that best thing we can do? Maybe not, right? This is one thing to do it, right? So it's very kind of intuitive way to do that, right? But drawback is, so we remove the high frequency component, okay? So that may not be very good, right? It depends on the application, really. For example, in like a camera system. So especially for video. For photo, maybe that's not the case, but for video, this is desirable. We always want an anti-aliasing filter beforehand, right? Because for video, if I have a high frequency component like my shirt, right? And then you'll see there's some kind of weird effect on this kind of, and then, if we get rid of the high frequency component, then there will not be this weird effect, all right? And for video, that may not matter. But for photo, it might be a problem, right? Because in photo, we need a high frequency component. We need the details, right? In most of the cases. Okay, a little bit editing may not matter much for photo, but for video, it's pretty undesirable. So in video, so if you have a a good camera, so who shoot video for or good photos, right? So if you heard of this, probably a professional video camera like maybe what's the brand? Blackmagic, or maybe in some Sony camera, I don't think they have it. For Blackmagic, I think. For maybe Nikon or some of the Nikon, so they have a called the OPF, optical OLP or optical low pass filter, right? So that's an anti-aliasing filter, okay? And then they can get rid of the high frequency component beforehand to make it better. Okay, very good. And so this is the concept of anti-aliasing filter, right? Just one way to remove this undesirable effect. Okay, so. Yeah, why it's not coming back? Come on. What's the problem? Yeah, let me reconnect. All right, and then we talk about reconstruction. Okay, so here, what do we mean by reconstruction? Is this, right? So basically, as we said, let's assume the signal is time unlimited and in frequency it's band limited, right? Even under this ideal condition, in order to recover the original signal, then we need sync interpolation, right? So basically, let's say this is our original signal and this is our sample signal, and then basically for each of the component here, we need to replace it by a sync signal weighted by this point, right? Look like this, right? So every point, so we need to put a sync function here, right, and sync function here, and so on, right? And then we add them up so we can have our perfect reconstruction, right? But for the sync function, there are two problems, right? The first problem is infinite domain, right? Basically, it means that it's time unlimited, right? So we cannot get a sync signal in practice, right? So that's the biggest problem. And the other problem is that a sync function, is symmetric around the zero, right? The zero axis, right? So it basically means that this is not causal. It's not a causal signal, right? Causal signal means that so all the signal has to be above 0 point. It cannot be anything below 0 point, right? So above 0 point meaning that we can actually implement the signal, right? But if something before happened before 0 point meaning the starting point, right? So if it has something below the 0 point, then it cannot be implemented, right? That's not ideal, okay? But this part is not a big problem because we can shift the signal, right? We can always delay the signal a little bit, right? Maybe we can ignore some of the the negative part of the signal, but normally for sync signal, right, it may not be a very big deal because as time goes by, the signal becomes very small, right? The biggest problem is the first one, the infinite domain, okay? So that's not ideal, right? It's not what we want, okay? So now we introduce a few ways to to get rid of it, right? The first way, so by the way, so this is this formula gives you the general reconstruction formula, okay? Ideally, so this P here is the reconstruction pulse. So ideally, P has to be a sync signal, right? But here, so we do not use sync signal because it's not practical. So we use something else to replace it. So basically, one easy way to think about it is just to connect everything together here, right? So that's an easy way to do the interpolation, okay? Of course, in this case, we do not get the perfect reconstruction of the original signal, but it's very doable and very easy to do. And actually, this is equivalent to say we use the PT equals to a triangle signal, okay? And the width of the triangle is TS, okay? So basically, this means that we replace each of the sample point by a triangle with the width of TS, and then we add them together, and then we have a linear interpolation. Okay? So this is one way to try it. But the problem here is here at this point, right? We have a sudden change here. It's not smooth, so which is not good, right? If I have sudden change here, it means that we have high frequency component in frequency domain, right? That's not very good. Okay, so this is one way that we can do this. Okay, so in practice, we may not want to do that, right, because of this sudden change. And another way to do it is called this kind of step signal, right? So we call that rectangle pulses. Now we try the duration with TS, right? And now this is what happened, right? Basically, what we do is that with every point we replace it by a rectangle signal, right? And starting at this point, right? Starting at the sample point, right? And then we can get this kind of interpolation, right? It's kind of step approximation of the original signal, right? That may not be, and also this is called zero order hold pulse. Zero order basically means that we hold it, right? The triangle case is called first order, right? Those are called zero order because we hold it, okay? And this is normal what digital to analog converter will do in practice, right? And again, for this kind of signal, you can see those points are not kind of ideal point, right? Because we have sudden change here, and then we have high frequency component, right? Which is not very ideal. And then, so we try another case. So where we shrink the size of the rectangle, okay? Make it smaller, right? And then what we have is something like this, right? So we have something very similar, but before, it's like they're all connected, but now we have a bunch of, kind of pulses here, right? And this is not hard to implement, right? And our assumption here is TP is much less than TS, right? Make it much shorter, all right? And what's the problem, by doing this? It's not also, it also has a problem, right? The problem is as follows. So basically, let's assume the original signal GF look like that in the frequency domain, and this is the PF, or this means, this is a sinc function of the narrow rectangle pulses, right? So because it's narrow in the time domain, so in frequency domain, so the first side lobe would be very wide, right? It's 1 over TP here, very wide. And then, when we use this, multiply the sample signal, not the top one, and multiply this with the sample signal, which is a periodic signal. So this is what we got, right? And now we can see, in the first kind of side lobe, so I have, in this case, I have 3 of them, right? So we need to pass that via additional low-pass filter to get the middle part out, right? The middle part is what we want, okay? But you can see here, so this is not a line here, right? It's not a flat line. So this is kind of, like this shape, right? So therefore, what we got in the end is like this, okay? And this is distortion, okay? It's also not ideal, right? So this is one of the problems, okay? So yeah, all of those are not ideal then. So the question is, what should they do, right? Because in practice, we can now do sync interpolation. We can do this, right? And we can do all of this, but they all have disadvantages, okay? They're implementable, but we cannot get perfect reconstruction of our original signal. Then what should we do? Okay, so we finish here in the makeup lecture, and now let's see what we're going to do. How can we deal with this distortion? Okay. Yeah, any questions? Right? So if you still have confusion, so feel free to watch the video. Okay, so yeah. And let's see what we're going to cover in this lecture. So basically, this is our lecture 26. And today, we're going to continue talk about the reconstruction to see how we can deal with the distortion, okay? And after that, so we're going to talk another concept, so which is called the maximum information rate in band limited signal. Okay, so this is basically to say as the follows. Okay, so in practice, you may heard, okay, so this is the bandwidth of a signal, right? And ideally, if I have more bandwidth, supposedly we can transmit more. Okay, but why is that? So why more bandwidth? Meaning we can transmit more information, right? So it's kind of very confusing. Yeah, one reason is that we didn't give you the metric of information, right? How can you measure how much we can transmit, right? This is one reason. And the other reason is that, so it's kind of hard to relate the concept of bandwidth and how much information we can transmit, right? So we may think, okay, so if a signal has, if we have more band to transmit, and then it means that signal, can have more bandwidth. More bandwidth meaning more changes, right? Sort of maybe have more information. But here we're going to give you a concrete reason why more bandwidth meaning more information, okay? And then, so probably we don't have time to finish talking about this. Probably we're going to talk about this next time, but this is all together. So now we talk about imperfect reconstruction, right? But in practice, we have, not practice, I mean now we have one more ideal assumption here, which is the impulse sampling, right? So reconstruction, we cannot do sync reconstruction. But for sampling, now we assume do the impulse sampling, right? Meaning that we can, we exactly get this point out, right? And with zero width in time domain. So that's not possible because in practice we don't have a direct delta signal, okay? How can we deal with this problem, right? How can we deal with this imperfection? So this is called non-ideal practical sampling. So actually, so this is extremely related to the first one. So there will be something very interesting happening that you may see next time. So basically, the approach to deal with the reconstruction is also the approach to deal with this as well. Okay, so we can achieve the same goal with only like one filter. Okay, we're gonna see how we can do that. All right, so yeah, so basically, let's recall. So basically what we got from the slides is as follows, right? So we can sort of have something like this, right? So that's our reconstructed signal. Let me see what notation I use. Yeah, did I use G tilde for the reconstructed signal? Yeah, I think I used G tilde of F. So this is basically, remember the original signal that we care about look like this. Right? Let's say it's flat, right? GF. Right? But now we have some distortion here going on. Right? How can we deal with the distortion? Okay, so maybe let me write down what the GF equals to. So basically GF tilde. So basically this guy equals to nothing but PF multiply GF bar, where the GF bar is the impulse sample signal. Okay, if we write it out, it will be like this: 1 over TS and PF, right? Where PF is the impulse shape. Sorry, is the reconstruction pulse shape, right? And then we have something like this, and GF minus KFS, right? So this is basically the formula that we're gonna reconstruct G tilde, right? So the real problem is here, right? So this causes distortion, right? So how can we deal with this problem? Right, so basically what is really happening is just like this, right? So basically, yeah, we have, make it from here to here, right? How can we recover it? let's assume this, right? Let's say, okay, this is what you got before, and this is what you got now, right? You know both of them. How can you, so they have equal weights, by the way, right? So can you recover this guy from here? Let's assume you know all the information you want. Right? In other words, right, this guy, so yeah, so this is kind of a low-pass filter, right? Let's forget about all the high-frequency component, right? Let's just care the middle part here, okay? Let's just care about this. PF times GF divided by TS, right? This is what you got for the middle part, right? And the distortion coming from here. Okay, let's say, okay, yeah, we can ignore the TS, right? Doesn't matter much. Let's say you have a PF times GF and equal to this guy, GF tilde, and you know GF tilde. You know PF. Can you get rid of the impact of PF? Exactly, just divide it, right? That makes sense? We just divide it, that's it. Right? This is what I'm going to say, okay? It's called equalizer, okay? But it's the simplest version of the equalizer. You can see in wireless communication system. So this may not be exactly what we do in practice. I'm going to explain the reason. But yeah, we can do some small variations of this, right? But the idea is just to divide. Because we multiply this guy, right? It's not ideal, we just divide it, that's it. Okay, of course, divide it, divide this part, in this bandwidth, right? We don't care about everything else. Okay, and this is what we're going to do. Okay, so basically, okay, let's see what is our idea. So this is very important, okay? So the idea, so the approach to undo the impact of it, so that's called equalizer, okay? And you may have heard of this word many, many times in communication, right? For example, if we consider wireless communication, so this function could be a channel, right? How to get rid of the impact of the channel? We use the equalizer. How to design equalizer? Just divide it by the channel, right? That's it. Okay, so yeah, so the idea is nothing but we add an equalizer filter to undo the distortion and remove the extra copies, right? Remove extra copies basically meaning that it also has to be LPF, right? The undo the distortion only meaning the middle part, right? But for the rest, everything else, we need to remove it. So basically, the idea is as follows, right? Mathematically, what we mean is as follows. So basically, we want to design a EF. Okay, so that's the equalizer in the frequency domain, right? This multiply G tilde of F, right? So this has to be equal to GF, right? Because GF is exactly what we want, right? But so, in practice, we may want something else, right? So we may allow a time shift version of GF. So basically, so we can design a signal such that we can have this kind of signal, right? So this is just a delay, okay? Okay, design T naught, to one, where the signal is, right? Sometimes it's important. So I say, and this is just a delay, allow a time shift. So one reason, for example, is that we want our result signal is a causal signal, right? We don't want anything below 0. Okay, we can make it causal, right? So let's say we can make it causal, right? Then we allow time shift, right? So this is what we want. And again, so this would be nothing but EF times PF, and then times 1 over TS, and then we do the summation over K, GF minus KFS, right? So this is what we got. Okay, and yeah, maybe let me redraw this a little bit. So you can see this is kind of low-pass filter, right? But just not the ideal low-pass filter. So it's a little bit more complicated, right? So let's see how we can design this exactly. Let's assume this is our GF. Okay, and let's say this is our GF minus FS, and this is our GF plus FS, right? And let's assume our bandwidth here is B, and here's minus B. And this will be Fs, and here is the Fs minus B. And this is what? So this is minus Fs plus B. And here is minus Fs minus B, right? OK, so now let's see how we can write our EF. OK. So first of all, so we need to completely remove this and that, right, and so on, right? So we have lots of copies of it, right? So it basically means that, so after this point, Fs minus B, right, everything will be completely gone, OK? So this basically means that we need to have a 0 here if Fs bigger than, not Fs, if F is bigger than this point, right? Absolute value of S is bigger than Fs minus B. OK? Right, and the next thing is that, OK, so how about the middle part? So the middle part, we need to make it exactly the, get rid of the distortion completely, right? Let's see how we can get it. So basically, what we want is that we need some scaling here, because here, so we have a 1 over TS, right? And then, so we need to divide it by PF. OK? Because we have something multiplied by PF, right? And then, don't forget this, this time shift, right? So basically, we just need to write the time shift here, Ej minus 2 pi ft naught. And that's it, right? We just divide the impact of PF, and then this PF multiply the PF here, right? It'll be gone, right? We don't have PF anymore, so yeah, very simple. And here, so we need to make sure when F is less than or let's say equal to B, then we need to have this exactly, right? How about the middle part, right? How about anything from here to here? So how about this part? Right? It's very clear that everything above here should be gone. Everything in the middle. So we need to make that exactly equal to that. How about this part? Don't really care, right? Because that is not, not within the band of our signal, right? So why don't we care about it? So it basically means that it doesn't matter, right? So we call that flexible, right? This basically means that when Fs minus B is less than or equal to F and less than B, right? So in this region, it doesn't matter, right? We don't care about it, right? Flexible basically means that we don't care about it. OK, so yeah, any questions? That makes sense? OK, so very good, right? Very simple idea to design a filter. Okay, now I see the problem. Right? What's the problem? Exactly. Problem is this, right? So we need to make sure, right, if we can do this, we need to make sure that within the whole range of this, it cannot be 0, right? So remember, it's a function, right? For continuous f, right? It's not just a 1 point or 2 point, right? It's a function. We need to make sure for the whole range of it, so it's not 0, okay? So we can, right? So basically, this means that so we cannot have PF equal to 0 when, right? Otherwise, it will be infinity, right? Not ideal. Okay, so now let's see for different pulse shape, right? We introduced 3 kind of pulse shape, right? So can this be satisfied? Right? For example, let's double check our so this kind of pulse shape, right? So which supposedly maybe should be the best. Yeah, I think I give you something causal, doesn't matter much. Let's assume this, we'll have TP over 2 minus TP over 2, right? And we assume the TP is much less than TS. In this case, it's very narrow pulse shape. Okay. And in order to double check it, we need to double check, its frequency representation, PF, right? And it's a rectangle path. Let's assume that is 1 here, okay? Then, so what is the frequency representation? Right, rectangle in time, so that would be a sink in frequency, right? Sink in frequency. And what's this point? The first zero crossing point. Yeah, very good. Yeah, just remember it, right? Because this happened too much. Okay, so basically this is a frequency crossing point, right? So what we need to make sure here, right? We need to make sure this point, okay, has to be bigger than this point, right? Then everything in the middle there will be no 0, right? Everything otherwise will be 0, right? So this basically means that, yeah, maybe let me write it here. So it's 1 over TP has to be bigger than B. Okay. So so that can we satisfy that? Right. Let's assume that we're sampling using a Nyquist sampling rate. Okay. So basically means that B equals to 1 over it's 1 over 2 TS, right? Yeah. So this, let's assume this is B, okay? So basically, if we replace that here and see whether that makes sense or not, so basically 1 over TP bigger than 1 over 2 TS, right? So this basically means that what? We reverse it, TP less than 2 TS. Is that true? Of course, right? So we assume TP is much less than 1 TS. Of course, TP is less than 2 TS. In other words, if we use TS here, not TP, so make it the width as wide as the sampling period, it still work, right? Basically means the narrow band, the narrow pulse, or a bigger pulse, both of them will work, okay? But the advantage of it is that if we use that, this will be very flat, right? It will make the design a little bit easier. Okay, because it's changing so slow. Okay. In other words, so we may assume this is completely flat, right? So roughly, so that will make the implementation a little bit easier. Okay, so that's basically how we do it, right? That make sense? Okay, great. Yeah, that's it for the first part. Yeah, let's talk about the second part. Yeah, the second part is the maximum information rate in a band-limited signal. Okay. Yeah, let's see how much information we can transmit. Okay, so basically, yeah, let's assume that. Suppose we have a stream of symbols, right, denoted by Gn, and n is all the integers, and so on. Okay, and we send those at the rate of 1 over Ts. Right. So basically, the GNs are the sample signals. Okay. So basically, we can see that so Gn is nothing but GNTS, right? So we just send a bunch of signals. Okay. So basically, now let's assume that we use the Nyquist sampling rate to do the sampling, right? So basically, in this case, it means that the Ts equals to 1 over 2b, right? In other words, so 1 over Ts, so equals to 2b. Okay? So yeah, maybe I can write it down. So basically, Gn is a sampled signal of this guy, right? And equivalently, we can write a GT as sum over this guy, weighted of this guy, and times all the sync signal, right, as original ideal reconstruction, right? So basically, you can write down this as Gn multiply the sync interpolation. Right, so we'll assume the ideal interpolation here, right? So those are the relation to what we have discussed before. Okay, so now basically we're sending a bunch of. So now we can just understand this. Forget about the physical meaning of it or the analog signal. We just assume that okay, we're gonna transmit a bunch of these numbers, okay, one by one. So this is what we do, right? So the goal is to see how fast we can transmit those. Okay, and so we treat each one of this Gn or this guy as a symbol. Okay, so now, so can you tell me how many symbols I can transmit per second? Right? How can we compute it? Right? We need to measure. So what is the time to transmit one symbol? Ts, right? Because that's the sampling period, right? So we need Ts second to transmit one symbol, right? And this will tell you for 1 second how many symbols that you are going to transmit, right? Okay, and then we can simplify this a little bit, right? So we have one symbol on the top, and then we can replace Ts by using this formula, okay, 1 over 2b. So yeah, this is due to the Nyquist sampling rate. And then we have 2b symbols per second. Okay, and that's it, right? So what does that mean? So it basically means that, right, just I'll repeat it. For 1 second, we transmit 2b symbols. And what is b? Right, b is the bandwidth of the signal. Okay, it basically means that if the signal has more bandwidth, so we can transmit more symbols. Yeah, more symbols probably mean more information. right? So this is our current understanding, right? We can make it more rigorous by using some concept from information theory, that we're not going to discuss it right now, but intuitively, this is how we characterize it, right? We assume all GN are different, right? They're independent, okay? So every GN will carry one symbol of information, and if I have more bandwidth, and then we transmit more symbols, and more symbols meaning more information. That clear? Okay, so now, so this is just for a baseband signal, okay? Like this, for a baseband signal, okay? Okay, but if we consider a double DSP signal, doubled sideband, signaling, right? So this basically means that if it's double band, basically means that we shift this here, and then we have another one on the other side, right? Basically, in that case, the bandwidth is doubled. We have 2B for the bandwidth, okay? So in that case, so we need to reduce it. So in that case, we just get B symbols per second. Okay, yeah, because the bandwidth is doubled. All right. Okay, so now let's explain what does this symbol mean, okay? So here it is related to digital communication, right? So yeah, before, every GN, so those are kind of from sampling, right? It's still part of the analog signal. But in practice, normally for digital communication, so every symbol, that's a discrete value. Okay, let's see what does these symbols mean. So you can more or less, forget this, right? So although they're related, but we're not going to relate them together now. So we're going to do that probably next week. But here, just give you a preview of what we mean by symbols. Okay, so for digital communication, you may have heard of, we measure how much information we can transmit in bits, right? So basically, now we measure how much we can transmit in symbols, right? So what is the relation between symbols and bits? Okay, so let's see what we mean here. So basically, in digital communication or in digital modulation, right? So which we have not talked about this yet, right? But just bear me for a minute, okay? So here we assume that each modulation symbol okay, again, so modulation symbol, we didn't talk about that, but now you can understand this symbol is basically the symbol that we are talking about here, right? Okay, so each modulation symbol conveys m bits of information. Okay, yeah, let's understand what does this m bit mean. Okay, so basically it means as follows. Using digital modulation with capital M, different signals, that can be sent. Okay. So basically, it means that we transmit only m different signals. Okay, no anything else, just m signals. Okay. In this case, m just equals to log 2 capital M. So and then we call that bit per symbol. Okay, let's see whether it makes sense or not, right? So basically, bit is a binary representation of the symbol. Okay, so let's consider one example that we can transmit 8 symbols in total, right? So basically, it means that 8 is m, right? M equals 8. We call that 8RE signaling, right? Which is not very common in practice, but it's good for illustration, right? So basically, 8RE basically means that m equals to 8. M equals to 8 basically means that in our system, we just transmit 8 symbols. Okay, so we have, let's denote the symbols as follows. We have S0, S1, S2, S3. Maybe I'll use another line here. S4, S5, S6, S7, right? So now we have 8 symbols. Okay, so basically, so in order to see how many bits we can transmit, we need to do this formula. Log 2 of 8, it means that we have 3 equal to 3, right? So basically, we use 3 bits can represent all of them, right? How to do that? It's as follows. We can use 0, 0 to represent S0, and then 0, 0, 1, 0, 1, 0, 0, 1, 1, and then you can use 1, 0, 0, so this is a bit, and 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, so basically every symbol will carry what? 3 bits of information. Okay, so that's basically how we can characterize it. Okay, and you can see, so for this kind of design, it's kind of very nice because you can see, so yeah, it's not that easy to see. So we need to rearrange it to see some nice property that we're going to discuss later. Anyway, so okay, so that is how I do that. So basically, yeah, maybe I'll just cover one formula. So there's something, some practical example about Wi-Fi that I can cover maybe in the beginning of next class using slides, so that'd be more efficient. I'll just cover one formula, then we're done for today. So in a practical system, let's see how we can compute how many bits we can transmit per second. Right here, we know we can transmit B symbols per second. Right? It's kind of trivial to see, how many bits we can transmit per second. Right? So maybe let's assume a practical system, such as, for example, Wi-Fi. Right? So the bandwidth is B. Normally, B can be equals to 20 megahertz. Right? So that's the smallest bandwidth for Wi-Fi. The largest probably 160 megahertz. Okay, so let's see how we can compute the number of bits per second. Okay, so basically what we do is that, so we use B symbols. Yeah, let's assume it's a DSP signal, right? So we have a B symbols per second. And then for one symbol, right, we can transmit m bits, right? We just use that, multiply m bits, okay, per symbol. Right, then what we get is B times m bits per second. Okay, and if you plug everything in here, let's say B is 20 megahertz. So 20 is a very common value in practice, right? We have 20 times m mega bits per second, right? So let's say if m, we use like QPSK, right? Probably yeah, we didn't learn that before, but let's assume, So QPSK basically means that we have 4 symbols instead of 8, okay? If you have 4 symbols here, then this formula will give you like 80 megabits per second. Okay, that's how we compute how many bits per second we can transmit, okay? And that'll be it for today. So we're going to cover QPSK later. Don't worry about it if you don't understand that. Okay, great. Thank you.